flexibility. And we're very honored to have Dr. David Larson here to chair the session. He is a senior data scientist at Tapestry. So David.
Well, welcome everyone. Thank you for sticking around. We think this is going to be a very exciting panel on a very hot topic. We've got 4 presenters today. We're going to run through each of the presentations, and unless there's any burning clarifying questions, we'll save the full Q&A until the end. One of our speakers, Amber Motley, who's going to go first. Fortunately, she wasn't able to travel, so she's going to be presenting remotely, and then we'll go through the rest of our speakers. But this is a great session. So we'll start with switching over to you, Amber, if you're ready to go. Yeah.
Let me share screen. And hi, everybody. Sorry I wasn't able to be there in person today. All right. So David, just give me a nudge when I get to that 18-minute mark for wave. I'll look for that.
Great. And we see a PowerPoint if you just want to make it full screen.
All right. You have the right version?
We're seeing the presenter mode, I think.
Okay. Switch it up. Is that the right one?
Yep. Amber, you're good to go, so take it away.
All right. Well, I am Amber Motley. I'm the Director of Short-Term Forecasting at the California ISO. And I'm excited to be here today to talk to you a little bit about large loads, but also demand flexibility as it relates to market design, operations, and data requirements. As we set the stage a little bit, the demand side of the equation is really going through a large system transformation. One of those system transformations that we see, which is what we're here to talk about today, is the large load side of things. But outside of large loads, you're really going through a transition of also having a lot of supply side resources on the demand side of the equation too. Those could show themselves with flexibility in EVs and V2G. They can show themselves with rooftop solar and residential batteries and co-located generation as well in that area. So as we go through the system transformation within the California region as well as the broader West, you really see the ability to create new opportunities to capture and scale that demand flexibility. I think there are new challenges as well as we go through that, and I'll talk about those a little bit today, and as well as the other panelists will as well. And a lot of them lead back to data and visibility gaps. I think one of the things that's fundamental in this system transformation is that the system on the demand side doesn't have the same visibility as you have on the supply side of the equation right now. And we'll dig into that a little bit more. All right, with that, I want to set the stage a little bit, and I'm going to try not to cough. If I do start coughing, I'll mute myself, but set myself the stage on the CAISO visibility as well as the market participation options that you have across the spectrum. So there are already what we call supply side resources or market participating resources within the California ISO market. And those are available to the California ISO BAA as well as the WEIM and the EDAM participants. And you can see them here listed as DER or DER aggregation. We also have reliability demand response and proxy demand response. I see those as market participating. There are on the supply side of the equation as it relates to the market optimization. But then you have other programs that are on the load modifying side or the demand side outside of the market participation. Those could be time of use rates moving elements around. They could be demand response programs that just don't participate in the ISO market and are like critical peak pricing programs that the utilities have. Then you have a spectrum that's kind of in the middle. And that's like emergency load flexibility programs. We've had a lot of emergency flexibility load programs we've seen within the CAISO BAA since 2021 and forward. But as you go through this spectrum of visibility, there's more visibility to those resources that are at this time participating in the market and on the supply side of the optimization versus those that are on the load modifying or the demand side of the optimization. So how does this visibility lead us to the ways they participate in the market? This chart is an eyesore. I'm not expecting to go through every piece of it, but it has a lot of great information as it relates to how you can participate in the market in the current design if you were a large load. Similar to the previous graphic on the left-hand side is the market models that would put you in the supply side. You could be in front of the meter resource or IFTM resource, which is a hybrid, a co-located, an NGR battery type. You could also be participating in the BTM side of it, economically through a proxy demand response, or reliability-wise through a reliability demand response resources. So there are pathways on the supply side of the equation of the market for the large loads to participate in the current form today. Similarly to above, the large loads can also participate on the demand side of the equation. In that demand side of the equation, in the current rules of the CAISO market, you bid your demand into the IFM or the integrated forward market. And then the CAISO forecast for the day ahead of the reliability unit commitment process, as well as all the real-time demand forecasting side of it. And we can perform the demand forecasting in two ways, and I'll talk about this a little bit more in detail on the next slide, which is the conforming versus the non-conforming demand forecast. Non-conforming and conforming demand have different pathways of participation, but it really still is on the demand side. And you're able to capture what that forward demand picture is going to be for the resources. I will note everything in the bottom blue box, just because today's a lot about visibility. Everything in the bottom blue requires some sort of actual to reference. It could be metering, it could be telemetry, it could be performance after the fact, such as the PDR and the RDR, but you have some element of performance and actual visibility that exists with everything in the blue boxes down below. One of the things that I think is really something to keep in mind as we go through the conversation, whether it is a residential battery resource or a large load, is the difference between a conforming and a non-conforming load. I think as a forecaster of demand, you're really used to forecasting the conforming load pattern. So what is that? A conforming load pattern is something that is predictable by weather, right? So if you want to form a relationship of 60 degrees Fahrenheit leads me to this demand on a Monday versus 60 degrees Fahrenheit leads me to this demand on a Sunday, you really have a predictable pattern that can be given to a model or algorithm to be able to figure out what that forward demand forecast is. That's what all of the tools, whether it be in the market or even in the demand forecasting space, are really designed for those conforming type loads. And they form the basis of the historical load actuals that are in the training the model, but they also form the basis of the forward forecast in the next 5 minutes as well as out 10 days. And they're the core to both the balancing authority operations as well as market operations because they feed into the market optimization as well. Non-conforming load, which is an example of an industrial steel mill, could be an example of a large load as well, a data center of types. They don't follow typical weather or time-based patterns. So on a Monday, they might be at 2 o'clock at 1,000, but on a Monday at 2 o'clock in the morning, they could be at 0. They're not really following the same predictable pattern over time, and so they tend to distort the forecast and create more error in the forecast if it still remains in the conforming load. So I think what we see today is that you do have a growing presence of non-conforming type loads within what I would call the overall conforming demand forecast. And that really is the great opportunity that we have to really think through and solve as we get better at predicting the next 5 minutes and the next 5 days with large load resources on the system. Similar to before, this kind of goes back to that chart that we saw of the different participation options across the top in the market. So this is looking at it from a market perspective and kind of across different data characteristics that you take into consideration. Are you on the demand side of the equation to the market, or are you on the supply side of the equation to the market? But one of the things that I do want to highlight from this graphic is that you have telemetry requirements for non-conforming demand has a telemetry requirement in its current state, and PDRs and RDRRs have a telemetry requirement if they're greater than 10 megawatts as well. I will note in the conforming demand forecast, which is the demand forecast that we create from the short-term forecasting side into the market, you can account for telemetry, but you also can have situations where telemetry is not there, and I'll talk about some of those as it relates to demand responses outside of the market. There's other performance characteristics that are there to monitor as it relates to the availability and the performance accounting between the different products. But one of the things that I think is important to note is the uncertainty forecast products. A lot of the grid operators have uncertainty products. That uncertainty product could be a regulation requirement. It could be for us imbalance reserve requirements, for flexible ramp requirements, and how they feed into the different products that are there. So you have uncertainty coverage in the conforming forecast. So uncertainty is really monitored for those net load characteristic elements that are in that conforming demand. You also have it indirectly, and it should say no star for PDRs and RDRs on the right-hand side, because even though it's on the supply side, it impacts the actuals, and because it impacts the actuals, it does have to be incorporated into the forecast. And if that cleared schedule doesn't perform, it does show up as conforming demand error, so it gets accounted for in uncertainty requirements. For non-conforming demand, something that is we're aware of is accounted for in the regulation requirements, but not the forward forecast of IR or FR requirements. Now it takes me a little bit into developing data requirements for large loads. We really are in the infancy right now of what those requirements look like, really keeping in mind this non-conforming load and the best way to integrate the non-conforming load into what we've holistically done as a conforming demand forecast. But as we get into what those requirements look like, I always like to look at real shapes. So on the right-hand side is a load profile. On the right top, you see load on the far left-hand side, and it goes from 450 megawatts to 650 megawatts, and time is on the bottom. So this particular load area within the Western footprint has really changed from 2022 to 2026. You see that from 2022, you were just below 500, peaking at maybe a little shy of 550 in this particular month. But as you go to 2026, that's changed significantly, and you're almost peaking at 650 megawatts. It's a pretty steady change where you see some years where the growth is bigger than others. The bottom graphic is talking about those conforming relationships. The model sees relationships of megawatt to something and forms a statistical relationship off of that. So take 60 degrees. This is dry bulb or temperature. 60 degrees forecast of temperature. The model's going to look at that and go, okay, I got all this data, 60 degrees in 2022 and 2023 should give me somewhere around 500 to 525 megawatts of load. Well, in its current day, now with 2026, 60 degrees can also get you over 600 megawatts of load. So if you're not doing anything to that forecast to help give it direction of what's causing this relationship to change over time, it's going to inherently form what I call a low biased forecast. It's always going to be low. In a training model, you typically have data spanning 3 years of historical data. 5 years used to be where we would sit. Sometimes there was 10 back in 2016. But right now, even if you had 3 years of data and you averaged out those last 3 years, it's still going to lead to a lot of error at 60 degrees Fahrenheit. So it's really important that you give that model some sort of information to be able to correct for what is going to be happening on the system and what is the demand going to be at 60 degrees Fahrenheit. Because if we can't capture what that demand forecast is, then at that point in time, it all ends up as uncertainty to the system that you have to be reactive to, not proactive to. We do know that we can account for information into the conforming forecast for non-conforming loads. We've proven this on the CAISO side with two different mechanisms. Demand response is the first one. Throughout the Western footprint of CAISO, as well as our WEIM and EDAM partners, there's a lot of out-of-market demand response. Those demand response programs we get schedules for, and those schedules can be put into the demand forecast to account for the drop as well as the increase of the load that's changing over time. Similarly, there are larger BTM or DER batteries within the Western footprint, and those schedules can also come to us and be incorporated for, as well as their actuals, because those resources have actuals associated with them as well, into the conforming demand forecast. So the information that you need, that you can put into the conforming demand forecast is a schedule of what is going to be happening, as well as some sort of actual information. It could be telemetry, but it could be after the fact actual information, which is what we get with demand response. So there is a proven record of putting that information and helping the overall forecast model that's there. You can see this over on the right-hand side of the graphic. Of course, we chose red and orange, which is always the greatest combination for a presentation slide. But in this case, this is a model, this orange line right here is a model that did not have the incorporation of the schedule within it, where the green had the incorporation of the schedule of the demand response in it, and the red is the actual. So you can see that the actual overall really follows the incorporation schedule and both the entrance of the reduction as well as the return, and really shows it doesn't have to have the lag that's associated with the typical autoregressive model. So what are the potential data elements that we're looking at to help support that visibility? And they really fall into 4 buckets. And I'm going to start with bucket 3 because it really refers to the previous graph I just presented, is 4 loads that have movement and variability in them. It's really important that you can capture what that schedule and actual is going to be so that that movement and variability can be incorporated into the demand forecast of what is the load going to be in the next 5 minutes, 15 minutes, 1 day, 2 days, 3 days. But it's also really important when you go back to those graphs where you saw the lines of 2022 to 2026 to see the load growth information. What's causing it to grow? How much should I expect it to grow by? Because then you can help true up the historical data that exists in the model over time so that you can still have data in the model and just treat it and know why it moved up in a way. We also know, and I know there's other presenters that are going to talk about this today, so I'll let them get into more of the details. Each one of the large loads comes with different effective operating profiles. And those operating profiles are really important information to be able to take into consideration with 1 and 3 that are there as well. Like, what is the baseline of the effective operating profile in combination with the growth information to really help that historical training set to get you to what the demand forecast would be. Then lastly, one of the things that we're finding are really important as well is just like a big generator on the system, there could be operating limits caused by transmission outages, whether it be on the transmission system, the distribution system, that could impact the ability for that resource to put out its full capability that day. Reminds me a lot of renewable resources and the curtailment of renewable resources or the dispatch of renewable resources. And when you dispatch them, you still need to know you're dispatching them and what their capability could have been for that historical training so you can forecast the next day, not taking into consideration whatever limitation could be there for those days. So those are the 4 pieces of the pie that we're really considering as we start thinking about what is the best way to integrate large loads within the market forecasting, of course, as well as the operational side of things. The last piece I'll touch on just in high level, because I know I'm getting close to time, is how and where we're doing that. If you're really interested in where can I go see more of this information, how is it going to evolve over time? We're really focused on a strategic vision where demand flexibility is reliably and economically integrated into the grid operations and markets overall. And that's really done through 4 pillars. We've talked about this before at ESSIG, and we talk about it a lot as it relates to the DER resources or the demand flexibility. But large load fits into this paradigm just like the DERs and demand flexibility resources. And the area that you see the information exchange, where we talked about today, really strengthening that coordination, both on the operational reliability side as well as the demand forecasting side, for both in and out of market large loads. It's also known that you're going to have in and out of market large loads as well, is through getting some element of automated information in a coordination framework between that transmission and the distribution interface for the coordination side. You can't do that without the other 3 pillars that you see here. Technology is really important. I think right now, a lot of that coordination that you see is coming in non-automated ways. Emails, phone calls, like this load came off. It is really important that we be able to automate the roles and responsibilities all the way through the data exchange and the security of that data all the way across that in the platform. And then, of course, you have the market design, which we talked about really early in the presentation, where you're developing or enhancing pathways of market access if the large loads want to participate in the market, whether it be through a proxy demand response or reliability demand response, or another element that's being worked on through the CAISO is potential demand side bidding. And that's really covered in what we call the DDEMI initiative across the board. And then, of course, we can't do any of this without policy and regulatory alignment, so we're coordinating very heavily with our fellow regulatory partners, the CPUC, as well as those across the West in the EDAM footprint as well. And with that, I will pause there and pass it back to David for the other presenters.
Really great presentation. We'll just, if there's any burning clarifying questions, we might have time for one. Okay, so Amber is perfectly clear. So Amber, we're gonna go to the rest of the presentations. There'll be the QA at the end, but yeah, it's great.
Great, thank you.
We're good. Great. So our next presenter will be Shiuli from Dominion Energy. So yeah, take it away.
Good afternoon, everyone. My name is Shiuli, and I'm an engineer in the Engineering Analytics and Modeling group at Dominion Energy. So today, I'm great to be here, and we were like learning a lot about probabilistic load forecasting, and now it's time to deliver a little bit about operational outage scheduling, how we are using load forecasting for that perspective in the electric transmission at Dominion Energy. So to frame the problem, let me start with the size of the system that we are supporting. Dominion Energy transmission serves territory across Virginia, North Carolina, and West Virginia. The transmission network includes 6,800 miles of transmission lines across multiple voltage classes, more than 1,000 substations, and roughly 50,000 transmission structures. So even before we talk about large load growth, outage scheduling is already a system scale planning challenge. So let's now look at the load in the system and how it's growing. So currently, as we see, like we have 70 gigawatt of large load requests over the next 10 to 15 years. And we can see that 25 gigawatt is already has projected connection dates throughout 2031, while another 45 gigawatt is under active study and future connection. On top of that, Dominion continues to receive roughly 10 new large load DP requests each month, which is about 2 to 3 gigawatts of additional requested load each month. So as we see, like earlier for the DP request, it used to come 10 in a year, but now we are getting it in each month. So the main issue is like how we can forecast the trend in future, and also in the larger horizon, like what it will be after 1 year and like after 5 years horizon. So therefore, systems operations requires precision outage and capacity planning in short-term and long-term horizons. The margin between load and capacity is narrowing, especially in the shoulder months where we usually take outage season we call it specifically. So in huge cases, increasingly need of forecasts that are not accurate but also explainable and decision ready. At the same time, transmission planning can also no longer rely on historical risk avert, conservative, over-engineered assumptions. So my message here, the forecasting is not only one product, it's a layered decision support capability. And we are moving from a world of one forecast that fits all, to multiple forecasts that can be customized for specific business decisions. So not all forecasts are built the same, and they should not be. So let's talk about operational outage planning, specifically from the perspective of transmission systems. So before the large load era, operational outage planning department only consisted of two groups. One is short-term hierarchical forecasting, and another one is hourly zonal forecasting for day-ahead short-term planning. So as a number of long duration critical outages are flooding the system, and the system is already heavily constrained at the moment, the need for operational outage planning also required to plan ahead. Therefore, we see the entire process is now a three-layered process, starting from strategic planning, long-term planning, and hourly zonal forecast for the short-term planning, where it refines the outage scheduling over time. So therefore, the overall objective is to schedule as many as outages as possible while maintaining system reliability. The need for forecasting is also different for each and every layer. Now I'll discuss in detail for each of the cases separately. So as we see for the strategic planning, which was not there before, and the group created recently. So the main purpose is to accommodate long duration critical outages beforehand. So specifically for the projects that require PGM approvals beforehand, like 500 kV reliability work or RTEP projects or line upgradation or substation upgrades, the scheduling strategy uses probabilistic load forecast to identify the best outage window by season. As the studies usually incorporate outage over 1 to 5 year out, the studies are performed at a system level. And we are looking at not only the bus level, but how we can accommodate outages throughout the entire system. And it helps us understand what scenarios to strategize the process of outage scheduling and also the approval from PJM. If a planned outage creates conflicts such as thermal or voltage violation, the first action is to shift that outage towards the off-peak season, given the load forecast, what we have. And these studies are ideally performed in monthly outage scheduling studies using the tool PSSC Terra and also Anod, which is another analysis platform built in where we can optimize those windows and find out the specific time for taking critical outages. So the major limitation in this case is like it can't accommodate area level studies. So for that, it comes to the next level or next horizon, where we do long-term forecast with our short-term hierarchical forecasting that considers medium duration outages up to 30 days at a bus and substation and area level. And for this, we need more granular hierarchical forecast, which can give us bus level, area level, and the county level forecast, so that we can understand the load growth within the next 1 year of horizon. They also consider maintenance and breaker profiling during that time. So the basic strategy is to reschedule outages whenever the conflict occurs, a voltage violation or a thermal violation. And the data center dense areas mostly where the PJM window, preferable window approval is needed. And in these cases, like winter is one important thing to consider, because ideally the outage scheduling times are during the off shoulder months. But for data center loads, as the winter temperature is not really affecting the load, so PJM gave us a particular new approval to take outages in that data center dense area. So rescheduling is not alone enough. Then we provide switching solutions and in between the areas. And in this case, forecast coherency comes into place, where this hierarchical forecasting is very important, because bus level needs to sum up to the substation level, and substation needs to sum up to the county level to understand what's happening in the area. So these are all time snapshot outage scheduling studies based on substation level coincidental peak loads using EMS state estimated. The main challenge is that this framework cannot fully accommodate uncertainty associated with future assets. Within a month, we don't know what new assets can be accommodated in the system. So now it's the horizon of near real-time outage planning. The final layer is where the final decisions are made and accommodated outages in the system. If we need to reschedule some outages in some other time using zonal forecast, that is a decision in making and try to prioritize the critical outages and rescheduling the short duration outages if conflict occurs. So it uses historical hourly load data and hourly weather forecast and the long-term zonal forecast, what we have provided in the first case. So produce an hourly zonal forecast within a 14-day horizon, which is a pretty short time forecast. And operationally, this is whether we incorporate the latest weather information to make it more outages, like making more understandable for conforming and non-conforming for off-peak days when violation appears. And also, like here the RAP criteria and the RAS criteria is in place, so that if certain contingencies appear, so we can just take out a little bit load and also like try to maintain the system reliability. And in other words, so this is the last mile for forecasting product that supports the final go or no go outage decision. So this is the forecasting framework what we use for our producing all types of forecast in the system. So data collection, exploratory data analysis, feature engineering, and then we do model selections, train a lot of models, then develop and reconcile forecasts using the hierarchical framework. And then we get feedback from our stakeholders, which is our operations and planning. For this case, specifically operations, and we then iterate again throughout the entire process. So it's a continuous improvement and continuous deployment process. We try to make changes and better data collection, better data acquisition, better pattern understanding, pattern and data cleansing every time when we iterate through this framework. So, but now there is one challenge in the system. So the last framework what I was talking about, so it's useful whenever we have historical data. So now we don't have historical data for some certain substations which are getting energized in future. So how we will forecast for those, and we need forecast to understand the load in the system and also like how they're ramping in the long-term trend. So in this case, we try to come up with one method, which I'll talk about in brief, and try to understand what types of loads are there in the system. So ideally, we have three types of data centers in the system: hyperscalers, co-location, and enterprise. And one of the hardest practical issue is the behind the meter visibility. So ideally, co-ops or the distribution companies who are our customers, they are not bound to disclose the nature of the load in the system. Therefore, it can be very difficult to tell whether a transformer is serving more traditional residential load pattern or data center type of load. So we don't know. There is a huge gap in communication. So that's where we try to capture the different load profiles using our SCADA data. And we found out that these shapes are really varying with these three statistics, mostly one: shape, range, and variance. And ideally, hyperscalers are very large facilities of and above 100 megawatt with relatively steady load profiles. But co-location facilities can be much more irregular and spiky because they reflect behavior from multiple tenants in the same facility. To address this problem, we defined three core features, as we said, and together these features can translate to raw transformer data into a more informative signature that can be compared across all the customers. And I'm showing the different types of load patterns, what we analyzed. And as we see, I kept the residential for taking an example. And ideally, there is one peak time in Virginia region, which is around 5 to 6 p.m. And in winter, there is a curve, which is, these are two separate seasonal curves. These are like specific, like typical residential patterns in the system. But now if you look at the hyperscaler data center, the range is very low. It's mostly stable profile. And it draws power more than 100 megawatt. And for winter also, it's not even getting affected by the winter temperature. So in case of the residential one, it's like whenever the temperature is down, then the consumption is up. But for this case, there is no change. And also for the edge and co-location data centers, it's a little bit more erratic as we were checking in the spiky load patterns. And also there is no peak load, like no understanding of peak load. It's like mostly peaking from 12 p.m. to 6 p.m., making the system more unpredictable. So now still we have more residential loads in the system. Probably 25% of the load is data center at the moment. But whenever in future a lot of like data center loads are coming into the system, they will overpower and we won't be able to predict these patterns in daily fashion. And also, like, we don't know when the data centers are going to get energized and if they are giving us the contracted capacity values, but not only they use the full amount, it's like a ramp pattern, which is not realistic. Whatever they do, they give us as a bulk load addition. So in this case, as we have seen, like some characteristics and some temperature correlation. And in this case, as we see, very less temperature correlation. And from here, how are we gonna forecast in for this substation? So this is under progress. So we are currently like doing some did the clustering analysis for each of these data centers, and then we are also trying to gather other information from the customers. Our customers are also like trying to help at the moment with more additional information, like with new ramp rates, and also like whatever the data center models, if we think about another perspective of it. But in this case, we can group those clusters and try to learn a distribution around it. And then given the new substations that are coming online in future, we can just grab them and try to sample from that distribution what we learned before. So and also like this study was done based on the SCADA data that was in the mostly like transmission level transformers. We took the data from there. But ideally for those cases, we can't exactly say like this transformer is feeding to data centers, because there are certain mixed load available too. So in this case, we can identify like probably majorly data center customers or majorly residential customers at that level. But here we are going more granular and we are trying to understand with the customer specific data, with our billing data, with everything else, like what are the patterns in the system to facilitate decision and support and load forecasting for those future assets. So thank you so much. It was a lot to cover within a short period of time. If you have any questions, please feel free to ask or email. Yeah, thank you.
Thanks, Shiuli. Any burning clarifying questions before we move on? Okay, well, we'll go to our next speaker, Sienna from ERCOT.
Thank you. Hey, everyone. My name is Sienna. I am an operations engineer within the resource forecasting and analysis team at ERCOT. So today we'll be sharing some of the observed behaviors that we've seen in some of these large loads and discuss some of the methodologies that we are exploring while forecasting these type of loads. So here are some ERCOT facts. We serve over 27 million customers within the ERCOT region. We cover over 90% of the Texas footprint. Our fuel mix is primarily natural gas, but in recent years, wind, solar has really, increased significantly with wind increasing, a few years back, and then now recently, solar and energy storage has really been catching up quickly. So we have set our peak demand record August 10th, 2023, with 85 gigawatts of demand. But in the recent past few years, that was the peak demand. We haven't broken the peak demand ever since. However, if you look at our average energy growth, that you can see that we have been has a steady incline, and we haven't, really slowed down ever since. So here's a plot that some of you may have already seen. It's kind of been a buzz to kind of discuss the long-term load forecast, right? So here the green bars are showing the kind of the base forecast. So that's your residential load growth, EV, PV adoption, and as well as cryptocurrency mining growth within the existing facilities. And then the blue bars is the submitted large load and medium load from the transmission service providers. So as you can see, that number is definitely growing. So to break that, down into a little bit more details, so we can see what are all of the types of load that's trying to interconnect. So definitely, primarily, the data center takes the center stage here, of course, but we also do see some growth in industrial as well as oil and gas loads. And of course, we also have the cryptocurrency mining demands, which is the main focus of today's presentation. Everything that we'll be presenting will be hyper-focused on the cryptocurrency mining demands. So just looking at the overall mining load behavior, we can kind of see two major factors that determine their behavior: price responsive as well as 4CP avoidance, or for coincident peak avoidance. So here I'm plotting the crypto mining load distribution based on different various system lambda intervals. So as you can see, for each bucket of system lambda, what typically do we see these loads operate at? So the plot on the left-hand side is for non-4CP month. I should explain what 4CP month is. So 4CP is the for coincidence peak program that we manage here at ERCOT. So that program is aimed to allocate the transmission cost for larger consumers. So if you are consuming during the peak demand for the 4 summer months, so that's June, July, August, and September. If you're consuming during the peak 15-minute system demand, then we will calculate your consumption as a percentage of the overall system demand, and then use that as a way to calculate your transmission costs for the following year. So going back to these plots, the plot on the left is non-4CP month, and then the plot on the right-hand side is a 4CP month. So you can really see that the non-4CP months here we see a very nice, correlation as the system lambda increases, the overall mining demand is decreasing. However, if you look at the plot on the right-hand side, what we see, okay, sure, we're still seeing some of that behavior, but if you notice that the lower ends of these distributions, right, these lower whiskers, they are very consistently dropping below 1,000 megawatts, despite the fact that the system lambda is, not even that high. So this means that, during 4CP month, the large loads, they want to curtail, they want to reduce, even if the system price is low. So looking a little bit more on the details of how they behave during those 4 months, here we're plotting the load reduction amount per day across the summer month. So here, each kind of this mountain that you see, the higher, that means that the more that they're curtailing, and each row is a day of the month. And then, that's just over 24 hours. So you can see that the load reduction pattern could be quite consistent during actual 4CP days or near 4CP days, right? If you look at these days in the later of July, every single day, the shape, the magnitude, the way that they curtail is consistent. However, there are still some challenges that makes it, kind of tricky to forecast when they will curtail. First of all, with the large amount of renewable penetration, it pushes the price peak towards the net load peak, right? So when we're talking about an operating day maybe having a tight margin, which causes a high price, we're talking about net load peaks. But the 4CP, the peak days is determined purely on the low peak itself. And also with the increase of battery storage, that also introduces a lot of variability, at least in the pre-RTC world, because 4CP settles on the settle load, right? So that means it's load minus battery charging megawatts. While the real-time dispatch operates on the native load. So what the market sees is what we call native load, which does not subtract that piece of battery charging megawatts. So what we have seen in 2024 is some of these loads, they see a peak day coming, they all curtail, and then comes 2 days later, it's another peak day, but it's less than the one that they responded, so they don't respond. But after we settle everything, removing battery charging, it turned out that the day that they all responded was a false peak day, right? So these are all very tricky, very small nuances that could throw a wrench in how we forecast these type of things. So the key takeaway here is, we definitely will need different models to capture both this price responsiveness of these loads as well as capturing their 4CP behaviors. So one question I think we get a lot is, well, how does these loads correlate with Bitcoin prices, right? So when we plot the daily average over the years between the Bitcoin price and the mining load, what we see, well, these two trends are generally trending together, right? They look very much correlated. However, does that mean that the Bitcoin price intraday fluctuation will impact how do they operate on a daily basis? Well, what we have found is not necessarily. So here we're plotting the very similar plots as the last slides. So again, it's system lambda intervals against the crypto mining loads, but on top earning days, top loss days, and top trading days, right? So we can see that, well, okay, so even though the Bitcoin price is fluctuating, but on day to day, at least within the day, the operation really is still following system lambda more than anything that's moving on the market side. By market, I mean the Bitcoin price, Bitcoin market. But one question is, well, what would this cryptocurrency load look like if Bitcoin price drops, right? And we have been seeing a significant drop in Bitcoin price in recent months. So we can see, yes, well, there is a slight decrease in the mining load. Roughly, since February, we see a decrease about 760 megawatts. But is that really due to the Bitcoin price dropping, or is that because of some other factors? It's still kind of too early to tell. But plotting again the same plots here, we do see that again how they operate day to day is still following system lambda more than anything else, which I think that does make sense, right? So Bitcoin price rising, that will incentivize them to build out their infrastructure, but once that infrastructure is there, well, they want to use it to their full capacity, while it's economically viable for them, right? Their real-time operating costs is mostly electricity costs, so that would make sense that they're still being more price sensitive than, following how the Bitcoin price is changing day to day. Oh, and if you notice here, we have a really big spike early in January of this year. Well, that's because of Winter Storm Fern. So during that time, what we observed is that these loads stayed consistently low for many days, for roughly 3 days, when the storm moved into Texas. So that's roughly the 24th to early morning 26th. So we can see that they not only curtailed, but they stay low until kind of the overall system low is coming down a little bit, and then you see them immediately jumping back up, and then the system low went up, and then they turned down. So that kind of went back and forth for a little bit. But, I think yesterday's panel and this morning's panels, we all talked about, what do we do when we see these kind of high impact but rare events, right? So this is another case of that. If we haven't really seen this type of behavior, the behaviors that we've seen is either 4CP avoidance, again, very consistent patterns of how much they respond and when do they respond, or, a high price response, right? Very sharp, very fast ramp rates. But these type of just staying consistently low, it's not something that we see very often. So how do we model these days better? And now I'm gonna shift gear a little bit to just talk about some of the forecasting methodologies that we are developing. So again, because of the growth in these demands, we really need to be careful about how do we detrend the overall demand, right? So back in 2023, when they curtail for 200 megawatts, that might be 40% of the overall system, overall mining demand. But now 200 megawatts, could be just 5% or something, right? So we need to kind of be really careful of how we detrend, and then so we can use longer historical data to train our models. And we also utilize another thing, what we call the energy storage margin, to calculate and use as a price signal proxy, right? So the ESR margin is calculated as the total thermal capacity plus solar wind minus the force outage, plant outage, and minus load. So this is kind of an estimation of how much ESR capacity we would need for the operating day. Well, why is a price signal proxy? It's because ESRs are kind of our price setters, right? So this is give us a really good way to tell, okay, estimate when they might curtail. So when we plot the two, the normalized demand and the ESR margin as a scatter plot, we do see this kind of positive correlation, right? So this is here plotted with just the non-4CP month. And what we did is that for, different intervals of ESR margin, we kind of just grab the slice of data and then look at what the distribution of the normalized demand look like and fit the distribution from that. And then during real-time operations, then we can start sampling from these fitted distributions and then to produce our forecast. But, of course, again, these low, high impact and rare events, when we don't have that many data samples to fit a distribution from, these might be questionable distributions that we fitted. So we're definitely exploring different ways to, either use some boosting methods or using some AI synthetic data generation methods to kind of boost the population of the data samples. So here are some results. Again, because the product of this model is kind of what percentage of their total capacity they're operating at. So we can simply use a recent low magnitude and then get back to megawatts, right? And then so we can also use the probabilistic forecast for wind, solar load, and force outage to create a probabilistic mining load demand forecast. So this is a snapshot forecast that we have produced. So this is on an hourly resolution, goes out to the next 7 days. The red is the actual, the light blue is the 50th percentile, and we also have the 20th percentile plotted in the dark blue. So definitely, we can see that overall we can capture how these loads fluctuate, but of course there's definitely some room for improvement. And quickly just want to touch on the 4CP prediction side. So really simply, we just kind of stitch together all the available information that we have. So using what has happened in this month so far and stitch together with our latest forecasted load as well as the historical load. So what has happened last year and then adjusted by the long-term load forecast to current day magnitude. Then we just do a simple ranking to see what is the highest 11 load days from this window. Then, so after the initial forecast has been generated, then if any of the days in the forecast horizon is in one of these top 11 days, then we can create a new demand curve that's generated by another fitted distribution from the responsive 4CP distribution. So here are some results that we see. So again, you can see that the on these near or on 4CP days, the behavior is consistent. That's what the forecast sort of reflected, which is, so far it's looking pretty okay, but definitely, again, some room for further improvements, especially those close to 4CP, but not quite, right? So these are the in-betweens that maybe price still comes, plays a role in this, or maybe some people are not so sure, not so confident about their 4CP prediction method. So definitely those times are quite tricky to forecast. So next steps and challenges. So definitely continuous improvements of our mining load forecast models, training separate models for 4CP month versus non-4CP month is top one priority, right? And then we're also exploring this hybrid model using classification and regression. So, use a classifier to say if today is going to be a high, medium, or low response day, and then use the output of that, put it into our regression. And so maybe if it's going to be a high reduction day, then maybe we can pick a lower percentile, right, to be more conservative. But some of the challenges, I think the previous two panelists definitely touch a lot on those challenges is, this continual shift in behavior, right? Either that's more mature for CP estimation methodology on their side, or, with the RTC market reinform, what has happened last year is probably not going to happen again this year. And some of these Bitcoin mining facilities, maybe a portion of them are retooling to go from Bitcoin mining to data centers. And overall, just the lack of unit level details for us to better forecast from bottom up, right? So how many of them have private power purchase agreements with generators? What percent of their facility is using an older, mining machine? And these are all kind of things that, if we had better understanding of those, it would definitely make the forecast better. And lastly, price, it's so important in modeling how these loads might behave. So having a price forecast will definitely help a lot. But forecasting price itself is such a tricky topic, right? When there is a capacity insufficiency versus congestion, these are all kind of things that I think the other panels have talked about, and definitely is something that is difficult to do. So yeah, I hope this presentation is really open discussion, and we just wanted to show y'all like what we have observed, and here are the challenges that we are seeing. So definitely still in the early stages, and if you guys have any questions or comments or just want to sit down and brainstorm, just feel free to grab any of us or shoot us an email. Yeah, thank you.
Thanks, Sienna. We're just gonna, give me 1 second to jump ahead. Oops, too far. Does it start, right? Yeah. So next we got Gabe from Verrus. So take it ahead.
Thanks so much. Glad to be here. For folks who know Jeff Bladen, I'm not Jeff. I'm his understudy. I'm head of energy policy at Verrus, and I'm going to jump ahead a little in the slide deck here, just because folks certainly know ERCOT and Dominion and CAISO, but they may not know. Let's see, where's the start of the general intro slides? They may not know Verrus. Here we go. So Verrus is a startup company working to build highly flexible and sustainable data centers, which in many ways, as I'll get to here, will hopefully be sort of responses on the demand side to the issues that are being seen on the operational side today. The folks at Verrus, many of them come from hyperscalers and data center developers who have done this in sort of the traditional way for data centers for a long time, and are now working to sort of re-engineer the data center from the ground up with a focus on energy use. A couple aspects here. I think all the slides will be posted, so if you want to dig deeper on any of this, there are a few things that should be live links in here. But Verrus uses a number of elements that are pretty innovative in the data center world. Low water consumption. We use closed loop cooling, not evaporative systems. Critical to the design here is battery electric storage. As I'll talk about, the current version of the electrical design integrates 4-hour lithium iron phosphate batteries directly into the electrical architecture, not just co-located, but really wired into the data center itself, which enables extremely rapid and flexible response. What we've termed power flow is really about getting more out of the nameplate interconnection to the grid. The way that, not necessarily germane to this panel, but data centers previously were historically have been wired in a way that reserves capacity for each row on a separate circuit, leaving some additional headroom. When that's added up, that reduces the amount of the utility nameplate interconnection that can actually be functionally used for compute after you subtract out cooling and things like that. A Verrus data center is designed with a 34.5 kilovolt internal microgrid, essentially, that allows for dynamic routing across each building, which essentially gets more out of the nameplate interconnection to the grid. So a higher load factor from the operator's perspective, and from the customer perspective, more compute available out of that interconnection. As a result of this, there's significant flexibility. We can talk more about how that can help create downward pressure on rates, I think, tomorrow with flexibility and interconnection, or you'll see some of these same slides again. And then also talking about on the operational timescale, Verrus has what's termed a StabiloGrid architecture, which is basically using the battery storage and internal electrical system to help provide a response to system frequency changes that help to avoid things in the millisecond timescale, like what we saw in Dominion a few years ago in terms of a lightning strike and then data centers tripping offline. When they sort of went over their internal counters and the number of seconds that were allotted for them. So basically, the overall goal of Verrus is to build data centers that are a grid asset, and we can talk more about any of the elements here, but really, this is all just sort of table setting for some of the elements that get to the operational piece that I will get to in just a moment. On the utility participation side, a Verrus data center is fully capable of being a firm demand response resource. This, of course, can help lower energy prices and can cause a more stable and predictable interconnection. And also the ability to add renewable generation. The battery really helps in terms of improving the flexibility and being able to draw from the grid if there are customers who are interested, or particular states who are interested in pulling power from the grid at hours where there's clean energy available, and then being able to use the battery to help cover hours when maybe less available. And we'll get back to this slide on sort of capacity component in just a moment. All right, I'm going to jump backwards now. So this will sort of get to some of the more nitty gritty now that we've run through who Verrus is and what we're trying to build. Okay, getting close. There we go. Just after CAISO. All right. So this is really about how a data center, I think one way to think about a number of the initiatives that are happening right now that you see from grid operators and from NERC with the essential actions is really trying to get the operational data and assurances out of a set of current assets that are becoming larger without necessarily changing their capabilities. This is sort of from Verrus's perspective, this is an opportunity to build from the ground up data centers that are able to sort of answer those questions baked into the electrical system from the start. So flexible loads, we'll talk more about flexible load interconnection again on tomorrow's panel. But part of the thesis here is that it's a lot easier to build large loads and computational loads as flexible and being able to provide meaningful operational data and response on the timescale that matters to the grid operator or balancing authority from the start rather than grafting it on after the fact. It is important to think about what the taxonomy of load flexibility is. There are a number of things that data centers can do to increase their responsiveness and their transparency. There is the ability to simply reduce load, and that demand response type of situation. And there are hardware and software means to do that. The hardware that Verrus uses means that from the customer perspective, they will hopefully not see any difference in their computational workload within the tolerance of the battery, as well as the ability to shift workloads in time and space, which I think there'll be some more discussion of tomorrow. So it's really important to think about a couple of elements here, and I think that all of the presentations from utilities and grid operators so far have gotten to these in some different ways in terms of what data centers can commit to on the planning time front, on the operational time scale, and also on the market time scale. There are some real differences in terms of what can be a compensated demand response resource and what can be more of a sort of rough justice type of simple curtailment of resources, potentially without compensation. That varies significantly. But we're really working to make sure that the data center architecture is able to respond to all of these in a way that is asset-backed, provable, and consistent enough for utilities and grid operators and regulators to be able to rely upon. A bit more here on what is sort of in this for every party involved, but I'm not going to dwell too long on that piece because I think this section here I want to run through very quickly, keeping an eye on the clock here. But again, this really gets to what commitments can be made at the interconnection phase for large loads as they're coming onto the grid. What is being built, what is being planned for, what is being committed to for the state regulators, for the grid operators, for the utilities in the service territory where they're being built, and making sure that those capabilities are being vetted and accounted for on the front end, not on the back end. This is probably fairly fine print up there, although maybe those screens might be large enough to read it. But really emphasizing that when these things are built from the ground up, they can really help to respond to a number of the NERC reserve needs, again, built into the large load in a way that is not simply a historic version of an inflexible large load, but one that is able to dynamically respond to grid needs. Now we get into some of the data requirements here that I think are going to speak more to and interact with some of what we've heard from other panelists up here in terms of being able to define what the electric characteristics are on a Verrus data center, what the peak demand, what the minimum demand looks like, what the ramp rates look like, and what the power factor are. All the elements and operational characteristics, which I'll get into in a moment, If there's a curtailment called for, how quickly does it occur? How long can it last? And how frequently can it be dispatched? And how long does it take for, again, a battery storage resource to recover from it? And then the grid support characteristics, and this is sort of on that seconds to milliseconds time scale of battery storage integration, if there's backup generation that's beyond the battery storage, what the EMS and telemetry capabilities and systems look like as well. So here is sort of the trust sheet here that we really see in discussions with utilities and grid operators. They want to understand these questions about what a flexible load is capable of. So trying to answer these from the perspective of a data center that, again, has a electric architecture that's integrated with 4-hour batteries. In the future, that could be changed as the storage technology evolves, but for now, 4-hour lithium iron phosphate. So if it's a hypothetical 100 megawatt data center, for the sake of round numbers here, that would be able to reduce demand in less than a minute by the entire scale of the data center. So the reduction is capable of being the full data center, which really can allow for integration in areas that might be grid constrained in a few hours a year. There's been a lot of discussion recently about grid utilization, which is an angle we're very interested in. Are there areas of the grid where this type of flexible capability can enable connection while providing assurance to the utilities and grid operator that they're not going to strain the grid at the time when it is most burdened. And by how much? Again, up to 100%. For 4-hour batteries, up to 4 hours. Of course, this is the usual battery arithmetic here, where if the depth of the curtailment is less than 100%, then you can multiply things out. If it's a 100 megawatt data center and you're only asked to drop to 50 megawatts, then you get 8 hours at that level. And then the recharge, I'm told by my engineers that it's a 0.25 C, so need to allow for 4 hours for recharge. But really, this is an area that I think, and I'll let my co-panelists speak to this later, but I think grid operators have become increasingly comfortable with by necessity for storage and hybrid resources on the gen side, thinking of energy limited resources where that have to be able to manage their state of charge. They have to be able to come up with their dispatch curve and include in that enough time to be able to recharge that will enable it to meet the next time that the system needs it. I do think this gets to some of the other questions, which I think are, again, echoed on the generation side, but maybe a little novel on the load side of what I've always thought of as the visibility versus dispatchability piece for the utility or the grid operator, which is what does the local utility or RTO need to be able to see for the load here, and what do they need to be able to actively control? I think those are active discussions there. I think in general, FERC has really come down on the side of letting storage resources be able to self-manage their state of charge is the sort of general rule here. But of course, we really do want to make sure that the telemetry is providing significant assurance to the grid operator that if they call on the data center 8 hours after the last event or the next day, if it's a multi-day heat wave in the afternoon, that it will be charged to the point where it's able to fully respond to that. And obviously negotiated into our service level agreement with any customer is being able to make sure that they have assurance that their computational workloads are not going to be interrupted. So we need to be able to balance those things depending on the exact topology of where we're plugged into the grid and the type of workloads that are being run at a given data center. So jumping ahead here to really the heart of it and keeping an eye again on the time. I know we'll get there in a minute. We want to convert these commitments into meaningful capabilities for grid operations. So a number of attributes here that, again, sort of using the NERC reserve products, which I think is timely because of the emergency action letter a few weeks back, making sure that we have clear resource qualification, visibility and control spelled out, making sure that there's consistent measurement and verification, as well as what the reliability requirements are. Again, all of these should look pretty familiar for anyone who's read the emergency action material or who's frankly looked at things like the MISO large load working group reliability requirements that are moving through the stakeholder process there. A lot of this stuff are areas that, because of the rapid growth in large loads, NERC and grid operators and FERC are having to grapple with pretty quickly. I think that baking flexibility in from the start makes it easier to meet all of these things in ways that give meaningful assurance to the folks who are tasked with maintaining the reliability of the grid. So some recommendations here by category. I won't run through all of these, but these provide, and you'll see these echoed in our comments on things at NERC and places like MISO, making sure that that things about timing, ramp rates, SCADA telemetry, what the availability and commitment periods, we sort of talked about that already, whether there's any seasonal change, how to handle measurement and verification, as well as reliability and compliance. And I should note the last item here is significant, that there are on the gen side, and there are non-performance penalties. And this is sort of a somewhat novel characteristic on the flexible load side, but one that sort of makes sense as the mirror image, that if there are commitments made to loads that look more like an actual market participant than a historic inflexible load, what the appropriate penalty structure might look like for not complying with those instructions. Again, this is only conceptually different as applied to loads. It's not a new concept on the gen side. This sort of gets to the last points I wanted to make on the overall flexibility and operational commitments here, which are when you start looking at operational and flexibility issues, not just in the seconds to milliseconds, being able to help participate in arrest frequency response issues or the sort of real-time markets piece, what can be reliably assumed by the grid operator for things like planning reserves, because those get to questions of what the overall system capacity needs look like. If you are able to have a large load that is meaningfully able to reduce its grid draw at the times when the grid is most stressed, that may make it easier to integrate onto the grid with less firm capacity being added for those hours that might otherwise be the case. Similar things may be true, and from our perspective, we hope will prove true on the network upgrade front, where if you're able to use the grid in hours when there is slack capacity available, and be able to rely on the battery backup during the long tail when there is additional, I guess it's the higher end here on this axis, when things are stressed, be able to operate flexibly and need to invest less in new transmission and network upgrades that hopefully allow the large load to come online more quickly. So I think that runs through most of the major elements here. We've got a little more on some of the reserve components and the capabilities here that that type of integrated electric architecture make possible, as well as the frequency response pieces. Again, I'd urge folks to look at our website for further discussion on the stability grid architecture that has been validated with National Lab of the Rockies and Verrus in terms of being able to respond to frequency events like we saw in Virginia a few years ago. But I think that generally runs through what I have in about the time I had to get there. So overall, I think the takeaway here should be that flexible data centers should